Welcome back to Upgrade to General, a series to help you upgrade your amateur radio license to general class. This episode is subelement G5, question group B, and I'm your host, Ron Call, KE7CR. This question set is about the decibel, current and voltage dividers, series, parallel circuits, sine wave, root mean square values, peak voltage, peak envelope power calculations. This question set has more calculations in it. Well, let's get started with the first question. The first question says, what dB change represents a factor of 2 increase or decrease in power? Well, a factor of 2 is twice. So double the power or half the power. And you just need to memorize that's 3 dB. The decibel is a logarithmic function. So if you look on this graph, you can see that 3 dB is double the power. Plus 3 dB is double the power. Minus 3 dB is half the power. So remember, every time you go up 3 dB, you've doubled the power. Next question, how does total current relate to the individual currents in a circuit of parallel resistors? Parallel resistors, if you imagine the current flowing from the source, the voltage source is going to be pushing that current. When it gets to the parallel branches, the current has to divide up into the branches. Now, if the branches were all equal resistance, the current would divide equally. But if they're different resistances, the branches with the least resistance has the most current flowing in it. So the answer for this question is it equals the sum of the currents through each branch. In other words, add up all the branch currents, it equals the total current. The next question asks how many watts of electrical power are consumed if 400 VDC is supplied to an 800 ohm load. Now VDC means voltage direct current, so it's direct current flowing here. These two laws are the most important laws in electronics, Ohm's law and Watt's law. I teach my students that Ohm's law is V over I times R, V for voltage, I for current, R for resistance. They didn't use C for current because C was being used for charge. Or it can be represented as E over I times R. Instead of V for voltage, they say E for electromotive force. Same formula, just two different letters to represent voltage. Watt's law is about power. Power is current times voltage. So it's P over I times V. So to solve this problem, you know you got 400 volts DC and an 800 ohm load. So you can solve for current using Ohm's law. You'd take 400 divided by 800. So on the calculator, 400 divided by 800, you really probably don't need a calculator. I set my calculator in engineering mode. It gives me 500 milliamps of current, or 0.5 amps. To find the power, if I know the current, I just times it by the voltage. So I would take 0.5 amps or 500 milliamps and times that by 400 volts and get 200 watts. Or you can rearrange the formulas here since current is just voltage divided by resistance. So I can substitute voltage divided by resistance for current in this formula. That tells me that power is going to be equal to voltage times voltage divided by resistance, or voltage squared divided by resistance. So V squared over R, or E squared over R. So 12 volts times 0.2 amps equals 2.4 watts. The next question asks how many watts are consumed when a current of 7 milliamperes flows through a 1250 ohm resistance. This time I'm given resistance and current, but not the voltage. But I can find voltage, it's just current times resistance. So 1250 ohms times 7 milliamps, but I don't want to enter 7 on my calculator. 7 milliamps is the same as 0.007 amps. Or if you've got a calculator in engineering mode, you can enter 7 and to the negative 3 exponent for the milliamps, and it tells me that my voltage is 8.75 volts. Once I know the voltage, I can times that by the current to get 61.25 milliwatts, or the answer approximately 61 milliwatts. Another way to solve this problem is by substituting the Ohm's law formula into the Watt's law formula. Since I know that power is current times voltage, but I also know that voltage is current times resistance, I can substitute the current times resistance in this formula for power. So power is current times current divided by resistance, or current squared divided by resistance. So 7 milliamps squared times 1250 ohms is also 61.25 milliwatts, or approximately 61 milliwatts. The next question asks, what is the PEP produced by 200 volts peak to peak across a 50 ohm dummy load? Let me explain what peak to peak means. When you're dealing with voltages of alternating current, the voltage rises from a zero value to some maximum value and then decreases back down to zero and then goes negative to some minimum value, then comes back up to zero. So it alternates. The voltage level never stays constant. So you could talk about a peak voltage, which is the highest voltage value that it reaches, from zero to the peak is the peak voltage. Peak to peak is from the minimum value or the lowest value that the voltage reaches in negative range to the highest value in positive range, which it turns out to be just double the peak value. Now, if you wanted to run, say, a circuit off of alternating current instead of direct current, since the voltage value is changing and the current is increasing and decreasing through that circuit, it's not going to stay at the same value all the time. So there's a value that essentially means the DC equivalent voltage. An alternating voltage that produces a DC equivalent voltage we call the root mean square voltage, or RMS voltage. So we ask, what's the peak envelope power produced by that across a 50 ohm load? Again, power is current times voltage, or since current is voltage times resistance, we can substitute that in, and power is also voltage squared divided by resistance. So this power equals voltage squared divided by resistance, though, that's for DC power. So that brings us up to the second problem. Because we're working with AC, in order to plug in a value for voltage, we have to use a DC equivalent voltage. So that would be the RMS voltage. So first, since we're given peak-to-peak voltage, we need to divide that in half to get peak voltage, and then multiply that by 0.707 to get the RMS voltage. So if we take 200 volts peak to peak, divide it in half, we got 100 volts peak, times that by 0.707, we get 70.7 volts RMS. Square that, and then divide that by the resistance of 50 ohms. And our answer is 100 watts. The next question asks, what value of an AC signal produces the same power dissipation in a resistor as a DC voltage of the same value? The answer is the RMS value. The next question asks, what is the peak-to-peak voltage of a sine wave with an RMS voltage of 120 volts? In this case, you're given the RMS voltage, so you divide that by 0.707 to get the peak voltage. When you do 120 divided by 0.707, you're given a peak voltage of 169.7 volts. So you need to double that to get the peak-to-peak voltage. And the peak-to-peak voltage is 339.46, so answer 339.4 volts. The next question asks, what is the RMS voltage of a sine wave with a value of 17 volts peak? So if you're given the peak voltage, times it by 0.707 to get the RMS voltage. 17 volts times 0.707 is 12 volts peak. The next question, what percentage of power loss is equivalent to a loss of 1 dB? Remember, 3 dB is double the power, so negative 3 dB is half the power. So if 3 dB is 50%, 1.5 dB would be 25%, so 1 dB would be a little less than 25%. So the answer choices are 10.9%, 12.2%, 20.6%, or 25.9%. The obvious answer would be 20.6%. It's less than 25%, but it's going to be greater than 12.5% if we went down to a quarter of that power. The next question, what is the ratio of PEP to average power for an unmodulated carrier? Well, PEP stands for peak envelope power. It's the highest power. Now, an unmodulated carrier means you're not changing the value. It's a maximum value as it is. So it's kind of a trick question in a way. The peak envelope power is the average power if your carrier is unmodulated. So the ratio is 1. The next question, what is the RMS voltage across a 50 ohm dummy load dissipating 1200 watts? To solve this problem, let's use our power formula. Power equals current times voltage, but also Ohm's law, voltage equals current times resistance. And we're going to substitute for current the voltage divided by resistance into our power formula. So our power formula becomes power equals voltage squared divided by resistance. But in this instance, I know power and resistance. So I'm going to rearrange my equation to say power and resistance equals voltage squared, and then take the square root of both sides, so I know that voltage equals the square root of power times resistance. So I'll take the square root of 1200 watts times 50 ohms. And my answer is 244.9, or we'll round it to 245 volts. That's the answer. The next question asks, what is the output PEP, or peak envelope power, of an unmodulated carrier if the average power is 1060 watts? Well, again, this is an unmodulated carrier, so it's already at the peak value. So the output peak envelope power is the same, 1060 watts. The last question asks, what is the output PEP of 500 volts peak to peak across a 50 ohm load? To do this one, we're also going to use a Watt's law formula, power equals current times voltage, and substitute our Ohm's law formula, current equals voltage divided by resistance, into the Watt's law formula. So we get our power equals voltage squared over resistance, because we're given voltage and resistance in the problem. In our question, we're given the peak-to-peak voltage, 500 volts, but we need RMS voltage to calculate the peak envelope power. So we're going to first convert our voltage, peak-to-peak voltage, into peak voltage by dividing it in two, and then multiplying that by 0.707 to get the RMS voltage. Power is voltage squared divided by resistance, so I'm going to take this answer and square it, and then divide it by the resistance, which is 50 ohms. And we're given 625 watts. That's the answer. So I know this section uses a lot of math. You really just need two formulas, Ohm's law and Watt's law. You need to remember the RMS voltage is 0.707 times the peak voltage, and you need to know what peak-to-peak, peak, and RMS voltage mean. Thanks for joining me for this section, and I look forward to seeing you in the next. 73, this is KE7CR.